Hello, my name is Philipp Witte, and I'm a researcher at Microsoft Research for Industries. In this talk, I will present our work on building new abstractions for cloud-native high-performance computing. Our work is motivated by bringing seismic imaging and inversion technology to the cloud. These workloads represent one of the most challenging HPC applications in scientific computing, as they involve repeatedly solving many large-scale partial differential equations to model wave propagation in the subsurface. Current industry stacks are mostly built around message passing interfaces, parallelize computations over individual shots or via domain decompositions. And these computations require massive scale on-premise HPC clusters. The cloud offers a great opportunity for supplementing on-premise resources, or it allows institutions that do not have access to on-premise supercomputers to run HPC applications. However, there are some fundamental structural differences between on-premise supercomputers and the cloud that HPC users need to consider. On-premise supercomputers are highly optimized for HPC workloads, which shows from the design of the network topologies and communication protocols to the choice of CPU and GPU architectures. On-premise clusters are optimized to provide low mean time between failures, high bandwidth, and low latency for storage and communication. In contrast, data centers for cloud computing are not specifically tailored towards HPC, but to support the broadest possible set of applications. As such, HPC hardware represents only a small fraction of all available resources in the cloud, and is oftentimes only available in a small subset of data centers. The good news is that new innovations in cloud computing are on the way. These innovations include hardware-accelerated networking for handling complex network topologies and communication protocols without taking away any CPU power from the user. RDMA over commodity Ethernet is another technology that's in the pipeline and will enable HPC users to build distributed applications with low latency communication on commodity machines. Apart from these innovations, public cloud platforms already offer a broad range of services for building HPC applications in the cloud, but using these services is challenging and it requires lots of vendor-specific glue code. In this talk, we present our ongoing research on building software abstractions for building distributed parallel applications in the cloud. Our work is intended to enable users to build applications with custom network topologies for combined data and model parallel applications, such as seismic imaging. On-premise supercomputers offer fixed physical network topologies that are optimized for HPC workloads and special communication patterns, while in the cloud, networks are virtualized and users have limited control over the physical location of nodes and how they are connected. For seismic workloads, we therefore suggest that it is advantageous to avoid clusters with all-to-all network topologies, which are challenging and time-consuming to set up, and which may create unexpected virtualization overhead. For seismic workloads, we can take advantage of the fact that computations are embarrassingly parallel over the data, and therefore work with resources that either use no peer-to-peer networking at all or only between a small subset of nodes. This scenario enables a combination of data and model parallelism in which we can still use MPI-based domain decomposition for individual PDEs, but take advantage of the embarrassing parallel loop over shots. We can implement custom network topologies for seismic imaging manually using cloud infrastructure. This approach provides users with a maximum amount of control and flexibility, but also results in a large management overhead. Services for batch computing enable users to build applications with combined data and model parallelism without having to manage resources and scheduling, which is handled by the cloud platform. However, users have to interact with batch computing services through vendor-specific REST APIs or software development kits, which are very different from the message passing interfaces or one-sided communication protocols that HPC users are familiar with. For this reason, we present a software framework in the Julia programming language called Redwood that makes batch computing services in the cloud look and feel like Julia's existing package for parallel programming. The motivation for Redwood is to bridge the gap between APIs for cloud services and distributed programming models that are common in data science and HPC. In the cloud, services such as batch processing are exposed via REST APIs, or RESTful software development kits. Building applications that use these services require a large amount of service-specific glue code, which is code that is not directly related to the application itself, but to how the application is run in the cloud. Managing cloud services can become quite complex, as we can see on the right-hand side, which shows the Python code for implementing a simple Hello World example with a cloud batch service. The idea of Redwood is to provide a user API that closely resembles Julia's existing API for distributed programming, as seen on the top left here. This makes it easy to take an existing application and run it via batch services in the cloud instead of using a parallel Julia cluster. To make it possible to run batch workloads using simple high-level code statements, Redwood uses Julia's macro programming and code generation capabilities. Redwood collects code that is tagged for remote execution and creates the required input and output bindings for managing data flow. When we remotely execute a function, Redwood captures and uploads all input arguments to cloud object storage, along with the modified code. Return statements are replaced with a serialization of return arguments, cloud storage, and we return a reference to these future objects to the users. Redwood's backend talks to various cloud APIs and SDKs, so users can write code that is platform independent and free of glue code. Redwood's current prototype supports only a single cloud platform, but its software design in principle enables support for multiple client backends. Abstractions, as we propose, make it possible to implement not only simple programs for batch processing, but also more complex network topologies with combined data and model parallelism, as we talked about earlier. In the example here, we sketch out how to implement these architectures with Redwood. At the top, we define a loss function, which takes references to a model and a single shot record as input arguments, and computes the function value and gradient. As these computations are embeddingly parallel for different input shot records, we can execute this function via a cloud batch service, and therefore tag it with the add_batch_def macro. Redwood provides the possibility to execute each individual batch task on a small cluster of interconnected nodes, which allows us to create an additional layer of parallelization within our loss function, for example, to implement domain decomposition via message passing. During execution, each batch task is managing its own small MPI pool, which only needs to persist for the duration of a single gradient. Next, I will walk you through a demonstration of how we can implement parallel workflows like RTM with the kind of abstractions that we propose. On the left-hand side, we will see what happens on the user side, and on the right-hand side, we see what is happening in the cloud. We start off with an empty batch pool that currently does not contain any nodes. We start by loading the Julia package and then create a batch pool. Users need to specify the size of the pool, which instances to use, and whether a subset of nodes need to be interconnected. These parameters are specified in a separate parameter JSON file. Instead of specifying the number of instances, it is also possible to start with an empty pool and enable auto-scaling, in which case instances are automatically scaled up and down depending on the number of tasks in the queue. Next, we define a Julia function that we want to execute in parallel using a cloud batch service. In this example, we create an RTM function that takes references to a shot record and the velocity as input arguments and returns the RTM image for the source location. When we define a Julia function with add_batch_def, Redwood collects the abstract syntax tree of this and all future tagged expressions so that they can later be uploaded to cloud object storage. Functions that are tagged with add_batch_def can also be executed on the local machine for debugging and testing purposes. By passing references to the data and model, we avoid repeatedly copying the model from the user machine to each batch task, and instead, each worker directly reads the model from cloud object storage. To upload the model from the user machine to cloud storage, Redwood provides a broadcasting macro, which serializes and uploads the tag variable to the object store. Redwood also creates the required resource bindings to give the batch task access to this data. The broadcasting macro returns an object reference to the user, which can subsequently be passed to remotely executed functions, which avoids repeated data movement between the user machine and the object store. Next, we can execute the RTM function via a cloud batch service. For this, Redwood provides the add_batch_exec macro, which is built in analogy to Julia's spawn macro for remote function executions. We call Julia's pmap function with the add_batch_def macro, which applies the RTM function to each element of the input collection, which in our case is a range of seismic shot records. Under the hood, Redwood captures and uploads the input arguments of our function to the object store, and modifies our previously defined RTM function so that its output is also written to cloud storage. Redwood then uploads the code, which is subsequently copied to each node on which batch tasks are executed. The actual compilation of the code happens separately on each node, or set of nodes if we use MPI. Redwood returns a batch controller to the user, which contains future references to the function outputs. One of the advantages of batch processing is that users do not have to wait until all nodes are up and running before you can start a job, as the batch scheduler automatically distributes tasks to whatever resources are currently available. Upon termination, each batch task writes its output image to the object store. As cloud batch computing does not support all-to-all communication, this functionality is provided by Redwood. Redwood provides a fetch-reduce function that applies a specified operation, such as a summation, to the output of the batch job. So in this example, this corresponds to the summation of all RTM images into a single image. To sum the function output, we take advantage of idle instances in the pool on which batch tasks have already terminated. As soon as two tasks terminate, Redwood creates a new task that runs on one of the available instances, and which sums two images and then writes the output back to the object store. Redwood assigns the summation tasks a higher priority than the original batch tasks, which means that these operations are executed as soon as instances become temporarily available. Once all images have been summed into a single image, only the result is copied back to the user. In the performance analysis, we present a weak scaling experiment in which we analyze the turnaround time for computing an RTM image for an increasing batch size of shots. The computational workload per node is fixed to a single RTM image. The turnaround time of a job includes the time that it takes to spin up the batch pool and the actual runtime of the tasks. The turnaround time is plotted in the left-hand figure, and each bar shows how much of the total runtime was used to execute the task, which is the actual time spent on the computations. The difference between the total runtime and the task runtime is the time that it took for the resources to start up. We compare the performance of Redwood with batch processing to the performance of a cluster manager. For the cluster example, the time to solution includes the runtime of each task and the time that it took to set up an interconnected Julia cluster. Instead of batch processing, the cluster example uses Julia's distributed programming package based on message passing. The middle and right-hand figures compare the individual components of the turnaround time for both approaches. The center figure compares the average task runtimes, while the right-hand figure compares the resource startup time only. Overall, we see that the task runtime with batch do not increase as we execute a larger number of tasks in parallel, as tasks are completely independent of each other. With the cluster approach, task runtimes are initially shorter, as we do not need to start a Julia session on each worker, which is the case for the batch approach. However, for an increasing number of parallel tasks, we see that the average task runtime increases, which we attribute to the fact that we have decreasing bandwidth as more workers dump their way field onto the distributed file system. Regarding the startup times on the right, we see that resources in the batch pool also start considerably faster. Next, we analyze the performance of executing an all-reduce operation with Redwood. Redwood uses a tree-based reduction in which idle instances sum two images at a time and then write the result back to the object store. Since summation tasks are assigned higher priorities than the batch tasks, summation happens in parallel as nodes become available. This means that if enough instances are free, Redwood is able to sum all images in log-n steps, where n is the number of total images to be summed. The optimal scaling is plotted on top of our elapsed runtimes in the figure on the right-hand side. We see that until 32 instances, the measured runtime closely follows the optimal curve, but then start to deviate for a larger number of instances. We attribute this slowdown to the fact that we are using a single storage account for our object store, which can only provide a limited amount of bandwidth. So in the future, we're planning to use multiple storage accounts, which may even be distributed across multiple data centers and therefore circumvent these bandwidth limitations. Abstract frameworks like Redwood can be used for embarrassingly parallel tasks like RTM, but the additional or reduce operations make it possible to build iterative workflows such as least square RTM or FWI. The power of abstractions makes it possible to combine different frameworks that talk to each other through well-defined interfaces, which enables users to build complex applications. Aside from geophysical applications, our approach can also be used for other applications with embarrassingly parallel components, such as deep learning or genomics pipelines. Bringing HPC workloads to the cloud is tough, as fundamental infrastructure differences exist between the cloud and on-premise computing centers. With our work, we introduce abstractions for parallel programming that make it easy for HPC users to program the cloud and build applications around existing services. In future work, we envision to extend our abstraction to a wider support of cloud services, such as serverless computations. We're also planning to support multiple compute regions to provide the possibility to scale beyond the capacity of a single compute zone. I'd like to thank my colleagues at Microsoft and thank you for your attention.